Hi everyone, welcome back, and we are going to pick up where we left off with our Physics and Driver's Ed unit. For this part of the unit, or this next little mini unit, we are going to be looking at the following physics standards, and so we're going to be focusing on what it means for an object to be in motion. And then how can we describe an object in motion? So we're going to be looking at things like the speed of an object, the direction it's traveling, the velocity, the acceleration, and the momentum. And then we're going to tie that together with our driver's ed unit by looking at what are the driving laws associated with speed, what are safe driving practices regarding speed, and why is speed an important factor in driving safety. So this first video here is going to introduce you to some of these physics concepts, and then you're going to do a couple activities where you're going to practice with the physics concepts and tie it together with the driver's ed part. So let's get started. First, I would love for you to please set up your notes. So you're going to open up to the next blank page as it says in the directions that are on the board, and you're going to make a 2-column notes sheet. And on the left, you're going to have the big ideas. And on the right, you're going to have supporting details. You may need to pause the video to do this. Just remember, as you're taking the notes, big ideas are things like definitions, major concepts, and supporting details are things like, the big ideas would be the vocabulary word or major concept, and then the supporting details would be a definition, maybe how to calculate something, a formula, etc. So let's go ahead and get started. All right, so in physics, especially this part of physics where we're going to be looking at Newtonian physics, it's all about things that are in motion or not in motion. And so first thing we need to do is sort of define what it means to be in motion. And I know that seems super obvious, but it really is a very distinct characteristic or definition of what it means to be in motion. And that is as follows. So here you have a big idea, and our big idea is motion. And you can add your supporting detail in that if something is in motion, it is changing position relative to a reference point. And the words relative to can also be thought of as compared to. Okay? So let's go ahead and look at what this might mean. Okay? So what do I mean by relative motion? So in order to, according to physics, and really we do this all the time, we just don't think about it. In order to determine if something is in motion, it must be changing position to a point of reference. So if you are changing, say, distance or orientation compared to some point of reference, you are considered in motion. So for example, if you were walking down the hallway, let's say I was standing in the hallway monitoring the hallway and you walked past me. I could tell that you're in motion because your distance, the distance from me, will change, right? So you are going to get farther away from me. That means you changed position compared to me. I would be your reference point. You could also pick another reference point, something like the lockers, right? So if you picked, say, locker number 25 and you got farther away or closer to locker 25, you are changing position compared to that point of reference. Okay, so it's pretty straightforward for the most part until you think about what happens if you are not so obviously in motion. Okay, so if you're sitting, or right now you're sitting in your seat, hopefully, would you consider yourself moving? And the answer is probably not, right? You're not walking around. Yeah, maybe your hands are moving and everything, but you're really not in motion. You're sitting still in your seat. However, you could easily put a reference point in there that would indicate you are moving. For example, if you were to use the reference point that is away from Earth, say the moon or the sun, right? So if you're sitting still on the Earth, right, the Earth is moving, right, around the sun. So your reference point being the sun, even though you're sitting still in your chair or lying down on your bed, you are moving compared to the sun. So if I was the sun and I was watching you on the earth, I would see you moving because you're changing position compared to me, the sun, the reference point. All right, let's look at some examples of what this might look like. Here, I've got my little scenario set up. Got a driving example here. And so let's first focus on the drivers, right? So here we have Edward and Bella in the car, and they are driving down the road, right? So as we can see, the car is moving compared to, say, the tree over there, right? So it is getting farther away from the tree. The car is moving, it's getting farther away from the tree. But couldn't we also say that Edward and Bella are moving? They are getting farther away from the tree, even though they are sitting still in the car, right? Kind of an interesting one, right? So same thing with you sitting in your chair and moving compared to the sun. Though they are not themselves causing the motion, they are in motion compared to the tree because they're changing position to it. Now let's look at something a little trickier. Driving down the road here, boop-a-doop-a-doo, right, Edward and Bella. Are they moving compared to each other? Let's think about that for a second. Maybe pause the video. Are they moving compared to each other? And the answer should have been no, right? They are not, even though the car could be going at 100 miles an hour, because we know Edward drives fast, they are not moving compared to each other because they are not changing position compared to each other. They're sitting still in their seats, riding along with the car. Okay. Also, let's look at Jacob's truck here compared to Edward's car. So we can see, if we imagine, because I can't move them both at the same time, if we imagine that they are both driving down the road at the same speed in the same direction, are they moving compared to each other? So is Jacob moving compared to Edward? And the answer is no. As long as they're moving in the same direction at the same speed, they are not moving compared to each other. Similar to how Jacob is not moving compared to his truck, right? And this is very important when we get into Newton's first law and why it's important to wear your seatbelt. Okay, now let's start describing some characteristics of things that are in motion. And one of the most obvious things, if we're going to describe things in motion, is how fast is it traveling? Its speed. So the speed of an object, how fast it's going, is the distance it's traveled in a unit of time. In math, you usually refer to this as the rate, right? So you've often calculated the rate, or you've used the DIRT formula, distance equals rate times time. It is the same formula, only arranged now to solve for speed. I do want to bring in another concept. In physics, the words speed and velocity are two different concepts. We often use them interchangeably in day-to-day life, but they are two different things. The velocity of an object refers to its speed, which we would think of, but also its direction. So if you were to describe something's velocity, you would always include its direction. So here I have an example. The car was traveling at a speed of 80 kilometers an hour, but its velocity was 80 kilometers per hour east. Seems very silly, but when you move up in physics, when you take it in high school, this becomes very, very important when you indicate that velocity, that direction. Okay, so let's look at how we calculate speed and velocity for that matter. Just remember that when you do indicate velocity, you have to have the direction with it. So speed and velocity are calculated by taking the distance that the object traveled and dividing it by the time. And so if we were talking about our cars here in the US, we would say something like we were driving 55 miles per hour. So we calculated that speed. We went 55 miles in 1 hour. In physics, we generally use meters per second or kilometers per hour. And so we'll be using those interchangeably this unit because when we're talking about driving, usually we're talking about miles per hour. Okay, so for example, if you could go ahead and calculate the speed of a runner who runs 5 kilometers, and I'm sorry my face is covering it up there, in 30 minutes. So runs 5 kilometers in 30 minutes. And you may need to pause the video to do this, and if not, go ahead and do that. You can also use a calculator. Okay, hopefully you got this. If you took, oops, get my pen back up here. Okay, hopefully you took the speed is distance divided by time, and that gives us 5 kilometers in 30 minutes. Now, ideally you would calculate this in kilometers per hour. Don't usually do kilometers per minute. So 30 minutes is a half of an hour. So if I did by 0.5 hours or 1/2 hours, I would get 10 kilometers per hour. If you did divided by 30 here, that's okay. You would have gotten 0.17 kilometers per minute, and that's okay. Okay, let's do a couple more practices here. You can pause the video as well. So here we've got distance equals 400 meters divided by 43.9 seconds. And so in this case, this is a runner running the 400. And you would want to do that, and you would get the speed in meters per second. So go ahead and pause the video and do that math. And hopefully when you got the answer, you got approximately 9.1. We're going to round to the tenths place since this is to the tenths place. 9.1 meters per second. All right, now let's do one more. Okay, so in this case, you're going to calculate the speed of a train that traveled 350 kilometers in 3.5 hours. So again, you take speed and its distance over time. So 350 kilometers. Make sure you carry those units. Divided by 3.5 hours. Okay, go ahead and pause the video and do that math. Okay, hopefully you got 100 kilometers per hour there as the speed of the train. All right. The last thing I want to take a look at is, of course, in science, graphs are very important. I want to take a look at a couple of speed graphs here. So when you graph speed, and we will be doing this, we're going to do a couple labs. Speed can be graphed as a line graph where you have distance over time. So it's just like the formula, distance over time. And let's look at what these two graphs mean. Okay, so if we have a very steep line like this, what does this mean? Maybe take a minute, pause the video, think about it, jot down some notes, see if you can think about it before I tell you. Okay, So hopefully you see what's happening here is that this object is covering a lot of distance in a short period of time. And therefore, a very steep line in a speed graph means that it's moving very fast. If I had a very bad at drawing straight lines with the mouse. If I had a very shallow line like this, you would expect that it's going very slow, right? It's not covering a lot of distance, but it's moving, but it's covering a lot of time. So it's moving very slowly. Now, how about this? It may be more obvious if I did something like this and then made it flat, right? What does it mean when the line is completely horizontal? Hopefully you can see that this means that the object is stopped. So when the line is horizontal, it's not moving forward in distance, but time is still going on. So the object has stopped at this point. So it was moving and then it stopped. Okay. All right, so make sure you finish these notes and then you're going to move on to the quick little review quiz right after this and then the practice. Good luck.